we start?
Yes.
Or okay, so I'll click now.
Okay, so thank you everybody for coming to this Nano Talk Volume 2. Thanks very much for being here, and it's our pleasure to welcome today Luz Maria Mejia, who is a postdoc at the MAUM in Bremen. She did her PhD in Spain at the University of Oviedo and was then a postdoc at ETH Zurich, and she's now a postdoc in Germany. And so without further ado, I'll let Luzma tell us about her exciting work on clumped isotopes.
Thank you, Clara, very much for introducing me. So today I want to tell you a little bit of how we did this work of developing this new proxy of clumped isotopes in coccolith calcite. And the stories, the very interesting stories that these new results are pointing at. The first one is regarding the North Atlantic as being potentially 10 degrees colder than what other proxies suggest during warm periods, and that perhaps coccolithophores are not necessarily always living at the sea, at the very surface of the ocean, but rather a little bit deeper. No. Okay, it's kind of slow now. So all the stories I'm going to be showing you today, all the data made part or were like originated during a Marie Curie project that I got and I started in ETH. And now that I am in MAUM, and I am happy to tell you that I am almost done with the setting up of the coccolith separation lab. I hope I will wrap up all the ideas that I started during my Marie Curie there in Zurich, and probably I hope I will show you new data soon. So obviously this I didn't do alone. I had a great group, great collaborators in Zurich that I have the luck to call them my family now. And now I have been adopted by a new family here in MAUM. And I will be working with them to produce this new data, and I hope I'll show you something. We'll have something new soon. So first, before we go into science, I want to tell you a little bit of myself. So I am originally a Colombian marine biologist. And if you have ever been to Colombia, you would know what I'm talking about. And if you have not been to Colombia, I would tell you go to Colombia. And if you don't want to go to Colombia, at least watch the new Disney movie, Encanto. So Colombia is a place full of colors. It's made up of colors. It's made up of life. It's actually the second most biodiverse country in the world. And I was marine biologist there. And as a biologist, and I really wanted to save the world, right? So, but as a biologist, there's so much you can do. Like you can fight for one species, you can fight to preserve an ecosystem in a given area, but there is so much you can do. And then I met Heather Stoll, and she, if you have ever met Heather Stoll, you would also know what I'm talking about. She's really good at selling her ideas. And she sold me the idea that if I changed from biology and I went to geology, biogeosciences, and climate reconstruction and paleoceanography, I would be helping to save all the species at the same time. I would be helping to save all the scholars at the same time because I would be fighting climate change. So this is the point where I am now. This is the real reason why I am where I am now and what I am doing, So, so why I am doing what I am doing is because I want to be able, that we are able to predict the climate response to greenhouse forcing so that we can actually react on time and save as much as we can from the mess that we are doing by putting up so much CO2 into the atmosphere, right? So that we can put the mitigation strategies that are necessary and do what we have to do. And now you all know what I'm going to tell you. So the way we do it in paleoceanography and in climate reconstructions is to go back in time to a time where we think was similar to what we expect in the future and try to understand how climate was responding to greenhouse forcing at that time. So for that, we have to be able to measure two things. So temperature, which is an indicator of climate, and CO2, which is concentrations, which is obviously an indicator of greenhouse forcing. So there are different proxies to reconstruct these two parameters back in time. I will just stick to CO2 2 seconds because we are going to focus now in temperature. But I just want to see, so this is a compilation that was recently done last year on CO2 data that are available until now. And I think the first thing you can see here is that the data are very sparse and there is a lot of work to be done so that we can actually understand where we are going in the future. I'm not sure you can, okay. So we can understand where we are going in the future. We need to improve our data in CO2. But now let's just stick to temperature because this is a presentation about temperature. So there are two families of proxies reconstructing temperature. The abiogenic proxies, which mostly are applied to foraminifera. So for example, delta-18O and magnesium calcium in foraminifera. But the problem about this proxy is that we also need information about the seawater chemistry back in the past. So in the case of delta-18O, we need the delta-18O of seawater. And magnesium calcium, we need magnesium and calcium concentrations of seawater, which back in the past are basically based on assumptions. So we are not completely sure how they were. So this is a problem, right? And then we have the family of the organic proxies, like for example, TEX86, which is based on archaea. And perhaps the main problem about this proxy is that we don't really are sure where the archaea are living. They could be living in the surface, they could be living in the subsurface, they could be even living down up to the seafloor. So where are we really getting this signal from? Where in the water column are we getting our temperatures from? So this is also a problem when climate models are going to use this information. And then we have alkanones. So alkanones are organic compounds that are produced by a family of coccolithophores, and we have no idea what they are used for. And this is perhaps the most widely used proxy for temperature. It's like the god of proxies. I call it like that. And perhaps the most, let's call it like the most shared problem, or about this proxy is that it's saturated above temperatures of 28, 29 degrees. So if we want to apply this proxy to warm tropical oceans, then we have a problem. And if we think about that, if we want to really go back in time to times where we're really warm, then we have an area of the ocean that is much bigger than, that is warm and much bigger than what we have today, right? So we have like this limitation of this proxy. But I think actually the most important problem that we have with these organic proxies is that we in our field tend to like a lot correlations. And so if it correlates to temperature, then we think it's a temperature proxy only, but we don't really like to go and mess up with the biology. And this is a problem because if there are other mechanisms that could be influencing one proxy, and if we don't understand them and if we don't know how they work, then we could have some information that is not actually reliable. So the problem about this proxies is that we don't really know how they work. And so, as if we want to predict how climate is going to be in the future, then we have the climate models. And for climate models to be reliable, they have to have good proxy data. So we are almost always assuming, yes, our proxy data is perfect. And then if something doesn't work out, it's the problem of the climate model normally, right? So it's boundary conditions that are taking into account the clouds, something's wrong. So in this case, this is alkanon. So this is an example here. And we see how climate model does really good at reproducing, let's say, the proxy data here in the Holocene, but it does not do so good, and I say so good like in, I don't remember how to call it in English, like in comillas, because it doesn't do so good here in the North Atlantic. And you see that the model data is suggesting that the North Atlantic 15 million years ago should have been around 10 degrees colder compared to what the proxy data is telling us. And normally we say, yeah, the problem is the model. But why don't we step back a little bit and we think, okay, do we really understand how our proxies work? Or perhaps they are not necessarily perfect and they are not necessarily applicable under certain time intervals or certain geographic locations or whatsoever. I think we have to step back a little bit and think a little bit more of where and how to apply them. So we were thinking, okay, how we have this situation, we have this problem, how can we try to help to fix it? So we thought, okay, clumped isotopes in coccolith calcite. Let's try to see what story this tells us. It's completely new, so let's see what happens. So why clumped isotopes? Perhaps the most important thing about clumped isotopes is that we know how it works. It's not like some other proxies that there are only correlations. We actually know how clumped isotope works. So clumped isotopes is when the rare or heavy isotopes of oxygen and carbon come together and form bonds, so 18O and 13C, and they form a bonding of mass 47. So it's more or less not that hard to understand. So if you heat up a closed system, like very, very high temperatures, let's say like 1000 degrees, then you have a system that is very chaotic. The bonds are vibrating a lot, so the strength of the bonds is very, very low. And so there is going to be less possibility of having bonds that are made up of these rare heavy isotopes, right? At very, very high temperatures. But then if we lower down the temperature a lot, then we have a more energetically favorable state. So the bonds don't vibrate so much. And the bonds that are formed have higher strength, and therefore there is more possibility of having more of these bonds of rare isotopes of oxygen and carbon. So it's pretty cool because you simply are depending on thermodynamics in the sense that if you have lower temperature, then you have more of these clumps, and if you have higher temperature, you have less of these clumps. It's all based on thermodynamics. So if I told you the story until here, then we would have a proxy that would be independent of seawater. So we are solving some of the problems that other proxies have. And then we would have also a proxy which is independent from biological overprints or vitals. So if the story was until here, then we have like the perfect proxy that solves all the problems from other proxies. But the truth is that there has been found some problems in some calcite or carbonate, with clumped isotopes. There has been found vital effects, for example, in corals, and therefore it's really important to be sure we don't have vital effects in coccoliths. So far, there has been so little done with coccoliths and clumped isotopes. There are only these 4 studies that have been published that we really need to focus on doing much more in this area. And perhaps all of this work has proposed or has found that there are no vital effects in coccoliths. Perhaps the most important one is the work of cultures from Gatz et al. In 2017. So they cultured coccoliths of 3 species, and they see, so you can see here, there's a big vital effect in oxygen, big vital effect in carbon, but there's not so much anything in clumped isotopes. Actually, it's inside their limit of detection. So they just report, we don't think there are vital effects in coccoliths. What I honestly think is what this data is telling us is if there is a vital effect, we are not able to measure it with the techniques we have now. So I really think we need to work more on this. There is work to be done, but we have to work with what we have, and this is what is published until now. So, okay, so we have solved why clumped isotopes. So now why coccoliths? Why not, for example, foraminifera? Because everybody is working with foraminifera, right? And they are bigger, they're easier. So coccoliths. So coccoliths, the nice thing about coccoliths is that it's ensuring that the signal that we are getting from temperature is from the surface. So coccoliths are photosynthetic organisms, and therefore they are forced to be either at the surface or a little bit deeper, anyway, where they have light to photosynthesize. So light has to be 1% of what they have in the surface or higher. Compared to foraminifera, who these organisms can move up and down in the water column, so we don't really know where the calcite is formed up. It's calcified in the water column. And the second important thing about coccoliths is that they extrude polysaccharides around their calcite, which protects them against diagenesis. So if the calcite is formed actually in the surface ocean, then we have like a warm signal, right? The original signal would be warm, but when they die and they sink down to the ocean, then they will be in cold areas. And if there is dissolution and recrystallization, then the calcite would be prone to a bias from diagenesis, because then the additional calcite would be colder than what it actually was formed by the original organism, right? But since they have these polysaccharides, they are less prone to diagenetic effects compared to other type of organisms, like for example, foraminifera. So it's more possible to have more preserved coccoliths in the same place as foraminifera. So now I'm going to show you which samples we use. So we have a great sample, a sediment trap sample in the North Atlantic, which is monospecific from Coccolithus pelagicus. The great thing is that it's monospecific. And we also have downcore samples from the last 16 million years from site 982. So as I told you before, one big thing about clumped isotopes is being sure that our calcite is well preserved. So we did some study about the preservation of our coccoliths, and we found it's pretty well preserved in all of our samples. So now we can just not worry so much about a cold bias from recrystallization in our coccoliths, and we can go on. So the next thing to solve is to get rid of the organic matter, because if we put organic matter in the machine, then we are going to have isobaric interferences, and then it will mess up with our clumped isotope measurements. So for that, we did it in 2 steps. First, we extracted the organic matter, which with methanol and dichloromethane, and in the second step, we oxidated the organic matter that was left there with H2O2. And the total lipid extract that we obtained from this extraction was afterwards used for calculating sea surface temperatures using alkanones. And for these, we just research all kind of calibrations that are around. So not only the baseline CORTOP and the most famous EHAX culture calibration, but all culture calibrations as well. Because obviously the best proxy to compare our new proxy is something that is also produced by coccoliths, so alkanones, right? So then after this, we get rid of organic matter, then we want to have coccolith separations. So we aimed at smaller than 11, 2 to 10, and smaller than 2 size fractions. Then for this, we used a centrifugation setting and semi-automated microfiltering. We developed a machine for filtering in EPH, which you see here in the left. And now here in Magum, we have 5 working machines. We finished mounting them like last week, and they are ready to start working. And in this study, we produced separations from 2 to 10, which are like the concentrated coccolith separations that are really, really, really nice. I'm super proud of these separations. I don't think there is a separation nicer than this that has ever been done for clumped. So I am super proud of this separation. So we really have pure coccolith separations. And now I'm going to show you the results. So first, the sediment trap. So here in the image, you can see where the bloom happened. And the nice thing about this trap is of this sample is that we have only 1 species, and we know exactly the temperature because we know where it was formed, and we know like geographically, we know where it was formed, and also in the water column. So we know exactly what temperature we are dealing with. And when we measure clumped isotopes, we get the same temperatures. Just always bear into account, we are always reporting 95% confidence intervals. So we have pretty much the same temperatures. So this is really cool. And what it's telling us is that at least for this species, we also don't see any viral effect or any suspicion of any viral effect, which agrees with the work of Katz. And also that at least for this species is a good tracer of temperature. Now I'm going to show you the data of the downpour in site 982 here. In the shaded part, you see the alkanone data with all the possible calibrations there are. So the lines are the 3 most used, let's say. And then I want you to bear in mind the gray area, which are the other culture calibrations people don't talk so much about, but they are there. And I want you just to take into account how big, how different, if you use one calibration or the other, these could change, this could be. And then here in the down part, I have the clumped isotope results. In blue, we have the smaller than 11 size fraction, and in yellow, we have the pure coccolith size fraction, so that 2 to 10. And something that is important to point out, perhaps, is that the results are very similar from these two size fractions, which mean that for this side, we didn't have to take out the very, very small fragments, which could have been altered by diagenesis. So in this side, probably not even the very small fragments that we cannot identify as coccoliths were affected by diagenesis, because they show similar temperatures as the coccoliths. So the first thing, maybe the nicest thing, is that we have very similar trends from alkanones compared to clumping coccolith calcite. So this is really good news. And obviously, the most obvious thing is that there are like around 10 degrees difference from between alkanones and clumped isotopes. So it's pointing us to a North Atlantic that could have been 10 degrees colder compared to what alkanones is, to the story that alkanones is telling us. Also, I want you to see that this difference is also observed in the modern Holocene sample here. This is the data from the sediment trap around, so you can see that clumped kind of agree better than what alkanones do. So we were thinking, okay, if we don't have a big issue with diagenesis, and if we think there are no viral effects, because it has been until now no reported to be viral effects, and we have information from our Coccolithus pelagicus that there seems to not be viral effects, also at least with this species, then how can we explain these 10 degrees? Because 10 degrees is a lot. So we thought, well, maybe alkanones are not working here in this place or here in this time interval. So we were thinking, okay, maybe there's not a problem with alkanones, maybe there's a problem with the calibration. And then we were thinking, yeah, for example, the baseplane actually uses the SSTs from summer and not from winter spring, which is actually when production is taking place. So it could explain a little bit of the temperature difference. But I would like to call you attention a little bit more on potential non-thermal effects that are usually not taken so much into account. Like, what happens if coccoliths are being produced in low light conditions? What happens with nutrients? What happens with growth rate? Is this really affecting or not affecting at all the alkanones? So I think, yeah, so this is the different stories that our different proxies are telling us. And if we step back a little bit and we try to see everything in a bigger picture, so here in this map, we have the sediment trap, site 982 and a tropical site. And here you see, so here is the story that the alkanones would be telling us. So pretty much the alkanones would be telling us that the globe 15 million years ago was a soup, that North Atlantic had pretty much the same temperatures as what we observe in the tropics. And here in square is the results from the model. So the model agrees pretty well in the tropics, but it doesn't agree at all in the North Atlantic. And when we compare to our clumped isotopes, which is the blue one, we see that it agrees much better with the model. So the story that clumped isotopes is telling us is, yes, the North Atlantic was warmer. Yes, there was polar amplification, but it was not a soup. It was not extreme. And if you recall the story I was telling you before, like why did I change the colors and the amazing and the diversity of being biologist, and I came up to work with white powder, pretty much because that's what we do. Well, this is the reason. When you find these kind of things, it kind of gives you hope that perhaps, yes, we are in a bad situation, but perhaps we still are able to do something against it. So finding this kind of things kind of pays off these kind of decisions, you know? So now I just want to show you an additional data set. We also measure clumped isotopes in different core top sediments. It's actually from the Holocene that are distributed around the globe. So we have a latitudinal, let's say, samples all around the latitudes. And in red, you see the clumped isotopes, again with 95% confidence interval. In yellow, you see the sea surface temperatures during the season of production of coccolithophores. And in green, you see the alkanones from the same samples. Here in green, the upper and the lower, let's say, end of the temperature is taking into consideration all the three most used calibrations. So EHOGS from culture, the baseline, and also the court of calibration. So the first thing you can see, and I am really happy about it, is we have a latitudinal gradient with CLOMT. So it's really happy to see, like, we have something that makes sense, right? This is super new, so anything could happen. So this is already something important. And the second thing, obviously, is that we have a difference with Eikenons and CLOMT, the same as we have with the North Atlantic sediment samples. And it's like around 5 degrees difference. So it's not 10 degrees difference, it's like around 5 degrees difference. And when we see a little bit more in detail, we see that for CLOMT isotopes, there are more differences. So they are colder, mostly in sites that are around the tropics. So in like warm oceans, they are colder. While in areas that are in higher latitudes, they seem to agree much better with sea surface temperatures. While Alkenons are overestimating in all cases the sea surface temperatures during the season of production. So this is just like making you ask, okay, what if actually coccolithophores were not living in the sea surface? Because perhaps in some areas of the ocean, they don't live in the very sea surface, which is what calibrations of Alkenons do. They calibrate to 0 or to 0 to 10 meters. But what happens if they live deeper? And so what we did is we just went down in the water column and we found where the temperature in that deep in the water column would be, the temperature that we find with CLOMT isotopes, and then we calculate more or less where the coccoliths would be calcifying. Where is this calcite being produced? For the tropics, it's actually much below the sea surface, while for the high latitudes, it's more towards the sea surface. That's the story this CLOMT data is telling us. And when we go to the literature, it kind of actually makes sense because, like, for example, data from these two papers that they have been transects across the Atlantic and transects across the Pacific, they have found a peak abundance of coccoliths up into depths of 200 meters, which is like a lot. So the question remains whether these cells are dead or whether these cells are living. So they don't really know. And the story that CLOMT isotopes is telling us is that perhaps they are living cells. Also, it's interesting from this paper in the Southern Ocean, they found that the light levels with which actually coccoliths are blooming in the Southern Ocean and phytoplankton in general are blooming in the Southern Ocean are like really low. Like if you compare these values to what we have in the surface, which is like orders of magnitude much higher, this proves that coccolithophores and the phytoplankton in general are able to use very low light conditions. And we always have to take into account that coccoliths don't only need light, right? They also need nutrients and they also need to balance against grazing. So it's not a constant. It's never a constant if you are working with living organisms. It's never a constant. You really have to take into account biology and ecology. I wish it was easy, but it's usually not. So for example, when you have a lot of light saturators could, light collectors could saturate, it also could damage the cells. So it kind of makes sense that in the tropics, the organisms could be living a little bit deeper or much more deeper than we would think at 0 meters. And in high latitudes, well, high latitudes is a little bit more complicated because right now, CLOMT isotopes, one of the main problems is that it's very hard to measure because CLOMT isotopes are in very low concentrations and therefore we have still very big errors, let's say. In a place where we have a temperature gradient, a thermocline that is maybe 2 or 3 degrees, so more or less the same error that we get with CLOMT isotopes, then it's very hard to point out where in the water column they're living. So what we think is that maybe in high latitudes, CLOMT isotopes would be more like an indicator of the temperature of the mixed layer, rather than where exactly they are living. And so, yeah, the remaining question is like, what can we do to make it better? Like in general, temperature proxies, but especially in this case, CLOMT isotopes. What are we missing? I think we are missing to be completely sure that there are no biofilms. This is maybe one of the main things. So I've mentioned the paper from Katzeran 2017. It's really interesting. We have big vital effects in oxygen and in carbon, and almost non-existent, let's call it, in clumped isotopes. But the thing is that these cultures were elaborated or cultured at very high light. So we have seen that coccoliths actually in the ocean can bloom at very low light conditions. So I think we should target like cultures that could simulate better ocean conditions. And why light? Why is light important? So if you put a lot of light into any kind of phytoplankton, also diatoms, they are going to shift, or they are going to potentiate the carbon concentration mechanisms, and pretty much you're changing the source where the carbon is coming from. And this could or could not, we don't know, affect the equilibrium of the formation of these calcites. So the idea was during my Marie Curie project to do these cultures, but we didn't have time. Also, the laboratories were not ready on time. But I'm really super happy to hear not long ago that they started cultures, and they have now results, and I really hope they will be out soon. Really excited to see how they are doing it in ETH. Also, I wanted to mention, I don't think I have this in this presentation, but in the 982 samples, we also separated samples of different size fractions, 3 to 5, 5 to 8, and 8 to 10. And we didn't see any significant differences between different size fractions. So I think it's also important to mention. And that second big problem with clumped isotopes in coccoliths is also a calibration. So is there a calibration effect? If you have worked with clumped isotopes, you know that there is a lot of arguing and discussing about calibrations, which one to use, are they all the same, are they not all the same? So here in the left is the regression we did with our core top samples. And when we plot all our regression together with all the other calibrations, like for example, here in yellow, you see the last abiogenic calibration by Anderson. In green, we have the last foraminifera calibration by Meinecke. And then in blue, we have the culture from coccoliths. They're not really different from each other. They're within error, this 95% confidence interval. They're within error. But the thing is that when you apply the coldest and the warmest of these calibrations, then you have up to 5 degrees differences when you put them in our data. So if we apply the warmest calibration, then yes, we would get more similar temperatures to what alkanones are telling us from our core top sites, but we would already be overestimating sea surface temperature. So I'm not really sure 5 degrees warmer, by having a different calibration, 5 degrees warmer, we would solve the problem. But most surely we would not solve that difference, the 10 degrees difference between alkanones and clumped isotopes that we are seeing in the North Atlantic. So I'm not really sure this is only a problem of calibration, but this is telling us we need to be more careful, and we need to do more research on understanding if there is a specific calibration that we should use for coccoliths. And going again back, yes, it's not only a problem of clumped isotopes, it's also maybe a problem of other proxies that we have to step back and try to understand, perhaps doing cultures to try to understand if there's a light effect, nutrient effect, growth rate effects, for alkanones as well. So yeah, this is my last slide. I want to take you back to this very interesting graph and tell you that if we don't put our forces together, then we are not going to be able to understand where we are going and how bad the situation is. And this is a call for all of you to let's do this together. Let's work together to try to find the solutions to these questions. And I think if we work together, we will be able to find the answers. And here I just posted a picture of the finished lab. We have machines working, we have centrifuge, we have everything. So you're very welcome. You can come here, I can teach you how to do it. And I would be really, really happy if we can just make this work together so that we don't miss the ship like the dinosaurs did. And we are in big problems. Thank you very much for your attention. if you have any questions, I'm happy to try to answer.
If you have any questions, you can either put your hand up or write it in the chat. While you're thinking, I can ask a question. Your core top data, which shows the latitudinal SST gradient with the coccolith clumped isotope data, I found really convincing and interesting. But if I'm thinking about the tropics specifically, so if we're reconstructing like 150 to 200 meters in the tropics with coccoliths, what's the hope that on geological timescales or orbital timescales we're going to be able to resolve surface temperature changes? So like if you have attended cooling at the surface,
I guess it wouldn't be surface, then we would be reconstructing deeper temperatures. And if we think, again, this is oversimplifying everything, which we tend to do a lot, but there is also no other way we can do it. If we tend to think that if we have bigger, let's say, tropical oceans that are like just not only in the tropics, but they are expanding, maybe perhaps we're also like, if we put together it's like a subtropical area or something, then perhaps we're also reconstructing something that is not from the surface, but rather a little bit deeper. It's a possibility.
But I guess if you're reconstructing over multi-million years temperature change, you're still going to get a signal that's outside of your error at 150 meters, if you see what I mean. You have to have quite a big temperature change in the thermocline for it to be resolvable with clumped isotopes, given the error on the temperature. So if you had a surface signal, then the signal would be bigger, and so you would have a better chance of seeing how much cooling there was. But if you're at 200 meters, then maybe you won't
you don't see it so much. Yeah, maybe you see it less. Yeah. So I guess this is the nice thing about doing it in high latitudes, because you're kind of targeting the mixed layer depth. But on the other hand, I didn't show this data because I haven't worked with them enough. But I have like 6 data points or something from back in the tropics, like in the Pacific. They are colder than alkenones and their other proxies. It's too cold. The temperatures we get are too cold, but they do make sense in terms of oxygen isotopes. So I have to say these separations, like the down core ones, were not as nice as the 982, which I think there will never be something as nice as that. So it was only smaller than 11. So perhaps there could be some so-called micarb that could have some diagenesis signal there. I think there is something we really need to take care when we are going back, especially in the tropics. But you can see something. So I know what you mean. If we are reconstructing down, then we probably don't see so much of a change. But we do see it. I guess it's just a matter of trying.
Just knowing what you're recording, basically, I guess.
Yeah.
Okay, there's a question in the chat. Can you say again why you record the thermocline temperature at the tropics and not at the high latitudes? Just because the vertical gradient does not really exist in the mixed layer of deep water formation areas. But then why do we record coccolith formation at depth? Does it mean that they don't really calcify at the surface?
No, wait, I don't understand.
Hang on, that's lots of questions in one go, Yannick. Can you explain again why you think that you're recording thermocline temperature at the tropics and surface temperature at the high latitudes?
We don't really know if we are recording surface temperature in the high latitudes because of the error of the measurements and the fact that the thermocline is almost non-existent. If we have an error of 2-3 degrees, we already could be like at 300 meters. So if they could be growing at 0 or they could be growing at 300 meters. We cannot point it out so precisely in the high latitudes. So that's why we tend to say, yeah, it records where coccoliths will be living, which is probably not deeper than the mixed layer depth. obviously not deeper than the euphotic zone.
Okay, so it's just the fact that you don't have a big upper ocean temperature gradient, which means that you are almost recording the surface, even if you're not.
Yeah, exactly.
Okay.
Yeah, and I mean, this could get better when we get better errors with clumped isotopes, but so far, like if technology gets better, this could obviously get better, but so far it's hard to pinpoint a point in the water column in the high latitudes, I think.
And so you think that the actual depth where the coccolithophores are calcifying is light dependent rather than anything else? And in the high latitudes, they're likely shallower.
I don't think that they're necessarily shallower in the high latitudes. I actually don't think so. I think they're just living in the mixed layer, whatever the mixed layer is during the time where they are blooming. I actually don't think they ever live in the very, very, very 0 meters, because it's just too much light. And I don't think they like so much light. And they're able to calcify and they're able to grow at lower light. So why would they just be there?
But also, they don't have much choice because they're constantly mixed around.
Also, the mixed layer, it's, yeah, also the mixing in the high latitudes is also bigger. Yeah.
Okay. Are there any other questions in the Zoom room? Okay, there's another one here. Heather is asking, can you recognize dissolution in coccoliths that might affect your temperature proxy?
So far, dissolution has never been called as a factor that affects the clumped isotopes. So, of course, if you have dissolution, it's more possible, or it could be possible that there could be recrystallization, and there we have a problem. But the fact that we remove some calcite, especially calcite from such an homogeneous calcite, which is formed by coccoliths, because it's like formed inside and it just goes outside. It's like just one plate. Is not really, people don't think it's really going to affect the signal. But if you have removed already this layer of polysaccharides, which means you have removed it because it's getting dissolved, then they're also more prone to recrystallization, and then you have a problem there.
I just wondered because I believe this core was used for Midt-Brunner's dissolution event study. So there is a big change in calcite chemistry. So for forams, it's very affected. So I was just interested when you said these are very beautiful coccoliths and we don't think they're affected by dissolution. But would you, yeah, okay, that was the question. Would you be able to look at your coccoliths and say, oh yeah, these proxies may be affected by dissolution? But okay, that's a good point. You don't.
Recrystallization, yes. And yeah. I think that's another part of the problem, I think, because maybe Clara is super better at recognizing these things, but it would be great to be able to quantitatively tell how much we have of recrystallization. Like this can be done with other fossils, like for example, it has been done with forams. But it would be great to have a quantitative measure and not just simply looking at the microscope and saying, yeah, well, more or less we have this %. So this would help us to know really what the bias could be, right? We were working in ETH back in the days to try to develop a technique to be able to hold coccoliths and polish them and make a cut and try to quantify which parts of the crystal are in the original setting and which parts could be recrystallized, so they are formed in different settings. But it was just impossible to hold the coccoliths in the epoxy, and so coccoliths would be polished off, or yeah, it was just impossible to hold them because they are so freaking small. So yeah, that's something also that we should investigate a way of doing it quantitatively. It would be so much better than just to have models of how much it could be affected, but to say, yes, 2 degrees, yes, 1 degree, yes, 10 degrees. Yeah.
Okay. So we have Yelena in the chat who's saying that they have investigated the surface microlayer of the ocean, and they've recorded lots of coccolithophores in it that were mostly in the haploid phase. So these are more adapted for high UV.
Haploid are the ones that are not calcifying? Can you remind me?
Doesn't have a microphone.
Oh no.
Oh no, it's just the life phase. I don't think it's to do with whether they're calcifying or not calcifying when they're haploid.
Yeah, but it doesn't really matter if they
were calcifying.
Okay. Okay, yeah, that's important, because if they are calcifying, then we're going to record it in our signal. If they are not, then we don't really care. Yeah, perhaps, I mean, like, biology is so amazing that we could have things that are able to adapt to high UV and things that are able to adapt to low UV. Yeah.
I was wondering if you've ever done paired coccolith foram clumped isotope measurements in any of your samples to see if your foraminifera record a warmer SS. If you choose a surface foram species like Ruba or Seculifer, if that records a warmer temperature than your coccoliths, or if it's the same.
Not yet, no. Would be kind of not hard to do though.
No.
I mean, I think it's really right now kind of easier to pick up forams than to get. It's not really difficult to separate coccoliths. I think the problem is that if we are not sure if there are diagenesis pieces, diagenetically affected pieces, then we really have to get to a very nice separation. Otherwise, we could just filter at 11 or 10, or just try to get to that limit where we get rid of foram pieces and pieces that are not coccoliths. But the real problem, time speaking, in the lab is to get rid of the small fragments that we cannot recognize. That's really time consuming. So yeah, it would be really nice to know if, are these pieces affected or not? If they are not affected, then we go on with an easy methodology. If they are affected, then we really have to try hard in the lab to get rid of those.